Hello everyone, today in Calc 3 we're going to talk about Stokes' theorem, but before we get to Stokes' theorem, let's revisit the curl of a vector field. So we talked about this before when we discussed Green's theorem, but just to remind you, if we have a vector field whose component functions we're going to call PQR are differentiable, then we can define the curl of f, either writing curl of f as notation or this del operator cross f as notation, either one represents the curl. And we can set it up as a determinant where here we have these partial differential operators in the second row, the component functions in the third row, and when we multiply, so let's say I multiply this operator by r, it's not multiplication, it's the operation of taking the partial derivative of r with respect to y. So then that gives us, if we take the correct partial derivatives, this vector, which is the curl of our vector field. So that's the curl of f. So we've seen the curl before, but let's explore some more properties of the curl. If f is conservative, that means we can find a potential function f, lowercase f, such that the vector field f is equal to the gradient of the lowercase f, the function f. Furthermore, if we suppose this potential function has continuous first and second order partial derivatives, then if I take the curl of this gradient, then remember the gradient itself is the first order partial derivatives. So now I'm taking the curl of these first order partial derivatives. I'm going to get these second order mixed derivatives, where in each component I have the same mixed partial just with the derivatives taken in a different order. So if you look at these, they're just the mixed partial derivatives taken in a different order. And Clairaut's theorem says if these are continuous, then they're the same because it doesn't matter what order you differentiate if you have continuous derivatives. So we assumed we had continuous derivatives, so by Clairaut's theorem, this is 0, this is 0, this is 0, the curl is the 0 vector. So what this tells us is that if we have a conservative vector field whose component functions are continuously differentiable, then the curl of that vector field is 0. If we want to go the other way and say, well, when will the curl being 0 tell us we have a conservative vector field? We need to assume the same kind of hypotheses we assumed when we talked about conservative vector fields in section 16.3. So this theorem says if f is a vector field defined on all of R3, whose component functions have continuous partial derivatives, and the curl of f is the 0 vector, then f is a conservative vector field. We actually don't need it to be defined on all of R3. All we need is for f to have continuous partial derivatives on an open simply connected domain, which is what we talked about in section 16.3. So as long as we have continuous partial derivatives on an open simply connected domain, then and the curl of f is 0, then f is conservative on that open simply connected domain. Okay? So that's curl. Let's take another look at Green's theorem in the circulation curl sense. So remember, when we talked about Green's theorem, we were talking about two-dimensional vector fields, simple closed curves in the xy plane, enclosing some region in the xy plane, so everything was two-dimensional. And Green's theorem said that the line integral of the vector field along that closed curve, which we could write as p dx plus q dy, is equal to the partial derivative of q with respect to x minus the partial derivative of p with respect to y integrated over the region, so the double integral over the region. But this is just the kth component of curl. If we look back up here, it's exactly that last component of the curl, so you can write it as the curl of f dot the k vector being 0, 0, 1. Okay, so this was for two-dimensional vector fields in the xy plane. Now we want to extend this result, get a similar result for three-dimensional vector fields over surfaces. And this is called Stokes' theorem. So the statement of Stokes' theorem is as follows. Let S be an oriented piecewise smooth surface. As we go, I'm just going to remind you of what all of these things mean. Oriented means that S has two distinguishable sides, and we've picked the normal vector we're going to use. We have a choice of two. Oriented means we have that choice and we've picked one of them. Smooth means that the surface has a well-defined normal vector in the interior. We haven't used that terminology before, but what it means is that we can find a parameterization for this surface such that the cross product of the first order partial derivatives of that parameterization is continuous on the interior of your surface. Piecewise smooth means that our surface can be broken into smooth pieces. And the parts where it's allowed to not be smooth can be curves, right? So you can think of something that's piecewise smooth, a box, right? The sides are rectangles, so those are smooth, but they come together at edges, and on the edges it's not smooth. Or you can think of a closed cylinder. Along the side of the cylinder it's smooth, and the top of the bottom, those are discs, those are smooth, but where the discs meet the side, the cylinder part, you get these circles, those are not smooth. But the entire surface is piecewise smooth. So we have to have an oriented piecewise smooth surface that's bounded by a simple closed piecewise smooth boundary curve C with positive orientation. So to remind you what all of these things mean, for a curve to be simple, it means it doesn't intersect itself. Closed means it starts and stops at the same point, so it's some kind of loop. Piecewise smooth for a curve means that, well, smooth for a curve means that we have a non-zero tangent vector at every point, except maybe the endpoints. And then piecewise smooth means it can be broken into smooth pieces, so you can think of a bunch of line segments put together, or most of the curves we've talked about in this class, right? They're piecewise smooth. And positive orientation, we're going to come back to that in a second. Positive orientation by itself meant we went around the curve counterclockwise. Now we're going to require something slightly different that I'll talk about in a second. Okay, so those are what we need for the surface and its boundary curve. We're going to let F be a vector field whose component functions have continuous partial derivatives on an open region in R3 that contains S. So you know what it means for the component functions to have partial derivatives. We need them to be continuous not only on the surface, but on a region containing the surface, because remember when we talked about partial derivatives, weird things can happen if they don't have that wiggle room to be continuous. We can come up with weird counterexamples where things like this won't hold. So we just need an open region containing that surface. So we can just need to be able to go off of the surface a little bit and still have a continuous partial derivative. So if this is the case, then the circulation around that curve is equal to the curl, the flux of the curl across the surface. So we can relate this line integral with this surface integral. And that's Stokes' theorem. So going back to what I was saying about orientation, how we're going to change it slightly, the orientation of the curve and the surface have to match. And so one way to think about this, instead of thinking counterclockwise, clockwise, you can think that if you're walking along the curve, you always want the surface to be to your left. And then the normal vector to the surface has to be pointing the same way you're standing. So what does this mean? I have a couple of examples. So let's look at this surface first. If I'm given this surface with this normal, then that means I need to be standing in this direction as I walk along this curve. And in order for the surface to be to my left, if I'm standing upright this way, I need to walk around in this direction. Vice versa, if I was given the curve first and told I have to walk around the curve in this direction, then in order for the surface to be to my left, I'm standing in this way, so the normal is pointing that way. For this surface, let's say I'm told I have to walk along the curve this direction, and in order for the surface to be to my left as I walk along the curve in this direction, I have to be standing upside down on the curve. So that means the normal has to be pointing down. That's what I mean when I say the orientation of the curve and the surface have to match. Now what is Stokes' theorem saying? Similar to Green's theorem, it's saying that the circulation around C is the same as the rotational tendency inside S, or the work done by the vector field along this curve is the same as how the vector field is causing things to rotate inside the surface. Okay? And this is exactly the same as what we said in Green's theorem, except now, instead of just being in the xy plane, we're allowed to have all kinds of crazy surfaces. And instead of just integrating over regions in the xy plane, now we have surface integrals. All right, let's take a look at an example. So let C be the oriented triangle lying in the plane 2x plus 2y plus c equals 6. So the triangle is oriented in this direction. we're given a direction to walk along this triangle. Use Stokes' theorem to find the circulation of the vector field negative y squared zx around C. So Stokes' theorem, all of the hypotheses are satisfied. We're not going to spend too much time going through those, but the main point of Stokes' theorem is relating this line integral to this flux integral. And so when we see a problem like this, the question is, should we calculate the line integral or the surface integral? And if we just calculate the line integral, we're not really using Stokes' theorem because it asked us to find the line integral. So to use Stokes' theorem, we should really calculate the surface integral. But I'm going to do both in this example and then let you decide for yourself which one seemed easier. So first, let's take a look at the line integral. For the line integral, my first step is to parameterize these three line segments. So we've done parameterizing line segments most of the semester, so I'm going to go through this rather quickly. I'm going to call this my first line segment here. So starting at the point 300, going to the point 030. When I parameterize this line segment, I get this function 3 minus 3t, 3t0. T goes from 0 to 1, and I'm also going to need its derivative, negative 330. Then I parameterize this line segment going from 030 to 006. I get 0, 3 minus 3t, 6t, t going from 0 to 1, and the derivative is 0, negative 36. And finally, this line segment going from 006 to 300 is 3t, 0, 6 minus 6t, t going from 0 to 1, and the derivative is 30, negative 6. So if I compute this line integral, to find the circulation, I actually have to set up three line integrals. And so we know that to compute a line integral, I need the vector field on that line or on that curve dotted with the derivative of the parameterization. So for this first line segment, if I want to plug that into my vector field, I need to know what negative y squared is. Well, that's negative 9t squared. Z is 0. X is 3 minus 3t. And I dot that with negative 330. On the second line, negative y squared is negative 3 minus 3t squared. Z is 6t, and x is 0. And I dot that with 0, negative 36. And on the third line, negative y squared is 0. Z is 6 minus 6t, and x is 3t, and I dot that with 3, 0, negative 6. And now you see I have three integrals. I'm integrating all three with respect to t, and the bounds of integration for all three are 0 to 1. So I'm just going to go ahead and combine these into one giant integral and compute these dot products. If I am integrating with respect to the same variable and I have the same bounds of integration, I can just put them together. So now computing these dot products, in each case I'm going to come up with two zeros and only one non-zero term. So in the first one I get 27t squared plus 0 plus 0. In the second one I get 0 minus 18 plus 0. And in the third one I get 0 plus 0 minus 18. So really all I need to do is integrate 27t squared minus 36t from 0 to 1. If I do that, I end up with the answer negative 9, and I'm finished. Now, let's take a look at the surface integral. So for the surface integral, I need some way to parameterize this surface. And just to remind you, this surface was given by the equation of this plane, 2x plus 2y plus z equals 6. I'm just going to solve that for z. So if I solve that for z, I can describe my surface as z equals 6 minus 2x minus 2y. And I can just let this be some g of xy and let x and y meet by parameters. So I'm just going to integrate over a region in the xy plane. If I project that plane, this plane, into the xy plane, this is my region of integration. And this line is just y equals 3 minus x. So then in y, if I set up bounds, I'm going from 0 to 3 minus x, and in x, I'm going from 0 to 3. I need to take the curl of my vector field. So I set up these partial derivative operators. My vector field was negative y squared zx. I start taking partial derivatives. The partial derivative of x with respect to y is 0, minus the partial derivative of z with respect to z, which is 1. That gives me negative 1. that are negative. The partial derivative of x with respect to x is 1, minus the partial derivative of negative y squared with respect to z, which is 0. That also gives me negative 1. And then finally, I take the partial derivative of z with respect to x to get 0, and the partial derivative of negative y squared to get negative 2y. I subtract negative 2y, that becomes plus 2y. So the curl of this vector field is negative 1, 2y. Now, if you recall from our study of surface integrals, if I can represent the surface as a function of x and y, then I can set up the surface integral in this way, where I need to know what these partial derivatives of the surface is, but in this case, the partial derivative with respect to x is just negative 2. The partial derivative with respect to y is also negative 2. So now I'm ready to set up this flux integral of my curl. So p in my case was negative 1. Partial derivative of g with respect to x was negative 2. So I have negative 1 times negative 2. That gives me negative 2. Minus q times this partial derivative is minus negative 1 times negative 2. That's also negative 2. And then I just have the third component by itself, so that's plus 2y. So really I'm integrating 2y minus 4 over this region, where y goes from 0 to 3 minus x, and x goes from 0 to 3. So if I integrate with respect to y, I get y squared minus 4y. Then I have to plug in 3 minus x and 0, but everything disappears when I plug in 0. So 9 minus 6x plus x squared is 3 minus x squared. Minus 12 plus 4x is negative 4 times 3 minus x. I combine like terms. I just need to integrate this polynomial. And I get 1/3 x cubed minus x squared minus 3x. I plug in my bounds and I get 9 minus 9 minus 9, which is negative 9. So I get the same answer, and I should, because Stokes' theorem says I should. Now the question is, would you rather do the line integral or would you rather do the surface integral? And really it's a matter of preference. I would say for this problem, they're about the same amount of work. But in order to say that we used Stokes' theorem, we would have had to do the surface integral because it asks us to find circulation. In the next video, we'll do some more examples of Stokes' theorem.